In this video, we'll take a look at one of the non-idealities of an op-amp, input bias and offset currents. For an ideal op-amp, the current entering the input terminals of the op-amp is zero. However, for real op-amps, a small current flows through the inputs. The first stage of an op-amp consists of a differential amplifier. In this differential amplifier, a finite value of current flows through the base of the input transistors. Let's call these currents through the base of the transistors as IB1 and IB2. Due to mismatches, the currents in both the terminals, IB1 and IB2, are slightly different. Usually in datasheets, a term called the input bias current is defined, which is the average of both the input currents. The direction of IB1 and IB2 depend upon the type of transistor used. Datasheets also contain another term called the input offset current, which is simply the difference between IB1 and IB2. Input offset current can be either positive or negative. However, most datasheets tend to define input offset current as the absolute value of the difference. Input bias currents generally range from a few femtoamperes to a few microamperes and can cause a big issue in high-precision circuits. Each bias current is modeled by a current source tied between ground and the corresponding input terminal. Once we have modeled the bias currents, we assume the op-amp to be ideal again, which means it has infinite input impedance. Hence, we can assume the op-amp is ideal and incorporate the bias currents in our analysis. Let us study the effect of the input bias currents on the non-inverting amplifier. Note that, whenever we analyze an op-amp for a non-ideality, we assume one non-ideality at a time. Hence, while studying the effect of input bias currents on the op-amp, we consider all other parameters such as zero offset voltages, infinite input resistance, infinite gain etc. intact. As shown, IB1 has no effect on the circuit because it flows through a voltage source. The current IB2, on the other hand, flows through R1 and R2, which creates an error. Using the superposition principle, we first set Vn to 0. The current IB2 flows only through R1. This is because Vx is 0 by the virtual ground condition, which means the voltage drop across R2 is 0. Hence, Vout is equal to R1 IB2. Thus the input bias currents affect the value of the output. We need to find a way to correct this error as it can cause severe issues in high-precision circuits. Usually IB1 and IB2 are very close in value, hence for the remainder of the discussion we will consider IB1 is equal to IB2. We can fix the issue of input bias currents by adding a parallel combination of R1 and R2 to the non-inverting terminal. We use superposition to find the effect of IB1 on the output. Hence, turning off Vn, the current IB1 flows through the parallel combination of R1 and R2, creating a voltage of minus IB1 into R1 parallel R2 at the non-inverting terminal. This will be amplified and added to the output value. Hence, the total output due to both the bias currents is minus IB1 into R1 parallel R2, into 1 plus R2 by R1, plus IB2 into R1. If IB1 is equal to IB2, all terms cancel out and we get zero output. Hence, we have nullified the effect of bias currents on the voltage. That's all for this video. If you have any questions, please ask in the comments section below. Don't forget to like, share and subscribe.